In college algebra today, we practiced simplifying the radical, and then we looked at the beginning of how to factor. So to practice simplifying the radical, we had these 6 examples here, and we practiced them. So maybe hit pause and see if you can simplify them without help, and then look and see how I did it. The main thing here is we do not want decimals. So if it is not a perfect square, you don't want to type it into the calculator. A problem like number 1, yeah, type it into the calculator because you get 6. So you get 6 because 6 times 6 is 36. And that would be our answer. But number 2, if you type that in, you'll get 5 point a bunch of numbers. That's irrational. We don't want that number. So you need to break 32 down into factors and look for a perfect square. So for example, the best way to break it down is 16 times 2. Then that breaks into 16 and 2, and square root of 16 is 4. If for some reason you don't think of 16 times 2 first, maybe you think of 8 times 4. Well, 4 is a perfect square, but 8 also has a 4 in it, so you got to keep breaking this thing down. Like for example, I stopped over here because 2 isn't a perfect square, but 16 is. So back over here to the right, if I do 8 and 4, now I need to break that thing down to this. And since I have a pair of 4s, that comes out as just a 4. Or you could read it as 16 times 2, like I have on the left. Either way, the final answer is 4 square root of 2. All right, number 3, same idea. I need to break that down into 2, or look for a perfect square. So I would say 100 times 2, which becomes 10 square root of 2. All right. Number 4 isn't bad at all, but it's weird because of the x. So first off, you can break that into 2 square roots if you need to. And square root of 100 is 10. Square root of x squared, you know you have 2 x's there. So that means it's a perfect square. And the answer would be 10x. This one is pretty nice. Number 5, not so much. So what I would do is I would also break this one down to 2 things. Break that 50 down. The best way to break it down is a 25 and a 2. And then maybe write all 3 x's down. So the 25 comes out. It becomes a 5 square root of 2. For the x's, we need a pair to come out. So there's a pair. So that would look like that, although that's not wrong, but it's kind of weird. So I would prefer you write it like this. Let me retry that again. There we go. All right. If you're confused by me saying a pair, and I didn't do that with 25, know that I kind of skip a step there. It's on the top left up there. So that becomes 5 times 5 times 2. And the 5s are a pair that come out as a 5. Right? Hopefully you're good with that. All right. The hard one, the fraction. There are many ways to tackle this, and the way I would work it is I would simplify the fraction before I move forward. So 32 over 12, both divisible by 4, that becomes 8/3. So there's another rule to simplify radicals are not allowed in the denominator. Oops. So that means not only do I need to deal with that 8 up top, because it has a 4 in it, but I need to deal with that square root of 3 in the denominator, because that is really square root of 8 over square root of 3. Now there's a trick to dealing with it. If you multiply top and bottom by that radical, it'll disappear. So that becomes 8 times 3 all over 3. Let me rewrite that. It's barely off the page. Square root of 3 times square root of 3 is square root of 9. Square root of 9 is 3. All right, almost done with this guy. That breaks down to 4 times 2 times 3 all over 3. The 4 comes out as a 2, so final answer would be that. All right, I hope that makes sense. That is it for our radicals. Next, we went over how to take out a GCF from a polynomial. So I give you an example up here at the top. If we have 10x squared plus 15, I'm trying to find the biggest number that divides into both 10 and 15, and that's a 5. And then I want to take out as many x's as I can, but I'm limited by the smallest x, which is this guy right here. So that's why I only took out x to the first power. If I try and take out x to the second power, there's not 2 x's to take out there. You're limited by the smallest. So 5x is our GCF. And then these right here are the leftover factors. And what you need to do is you need to ask yourself, what would I multiply the GCF by, 5x, to get what we started with? So 5x times what gives you 10x squared? 5x times what gives you 15x, and that's where the 2x plus 3 come from. So let's try it on number 1. Biggest number that divides into 18 and 27 is a 9. And then for x's, you go to the smallest exponent, which is x squared. They both have an x, that's vital. But then you go to the smallest exponent, so x squared. All right, 9 times what gives me 18? And that's a 2. X squared times what gives me x cubed? That's an x. 9 times 3 gives me 27. And I took both of those x squareds out. X squared times 1 gives me x squared, so we're done. That is factored. In the future, I'm going to ask you, can we take this any further? Right there. But we can't, because it's not x squared and there's nothing to take out. So we'll look at other scenarios down the road. For this one, number 2, it is very weird. Think of this as one term, and this is a second term right there. So look at the 2 underlined purple things. What do they both have? They both have x plus 3. So x plus 3 is your GCF. So you take x plus 3 out, wrap it in parentheses, and then you write the leftovers from both of those underlined portions. So I took x plus 3 out, there's an x squared there. On the second term, there's a 5. Once again, tomorrow I'm going to ask you to see if we can take this portion further, but I'll tell you because of that plus sign, it's just not factorable. We'll practice that tomorrow. See y'all later.